This title tells us we'll learn how to tweak TSNE, T-distributed stochastic neighbor embedding, a fancy visualization technique, to get more reliable results. Think of it like fine-tuning a recipe. We're adjusting the ingredients, parameters, to ensure the final dish, visualization, is consistent and delicious every time. The core problem is that TSNE's results can change dramatically just because of the initial random starting point. It's like trying to find the lowest point in a dark, bumpy valley. Your starting spot significantly impacts where you end up. I can set a _random_state value. Think of this as using a map to navigate the bumpy valley. It gives the algorithm a specific path each time, eliminating the random element, so I get the same results every time. Increasing the number of iterations gives the algorithm more time to explore the valley and settle into the lowest point, making the final result less sensitive to the initial guess. It's like having more time to search for the lowest point in that dark valley. A lower learning rate makes the algorithm take smaller, more cautious steps in the valley. This can lead to a more stable result, but it's not a direct fix for the initial random starting point issue. It's like walking very slowly down a hill. You're more likely to avoid a bad path, but it will take a lot longer. Perplexity adjusts how the algorithm views its data points. Changing this doesn't directly address the problem of random starting points. Think of it as changing your perspective while looking at the valley. While it could give you a different, better view, it doesn't solve the problem of starting your journey at a random place. I'll explain this one first because it's the most direct solution. TSNE is a bit random, starting from different points each time you run it. By setting _random_state, you're giving it the same starting point every time, making results reproducible. Think of it like setting the seed for a random number generator. It's like making sure you always start a race at the same line. Now, let's talk about increasing iterations. TSNE is an iterative process, meaning it refines its results over many steps. More steps give TSNE more opportunities to find a good solution and reduce the influence of that initial random start. It's like giving a puzzle solver more time to work. The longer they have, the better the chances of solving the puzzle, regardless of where they started. A smaller learning rate makes TSNE take smaller steps at each iteration. This can make it more stable, but it's not a direct solution to the randomness of the start. Think of this as trying to find a specific spot on a map by taking smaller and smaller steps. You might get there more slowly, but it might not solve the initial uncertainty about your starting location. Perplexity adjusts how TSNE considers data points' neighborhoods. Changing perplexity primarily impacts the embedding quality, not the stability due to initial randomness. It's not the main lever to control that initial random start issue. This is the main question, leading us to explore ways to improve TSNE stability. The options provided are parameters that you can adjust to control the algorithm's behavior and therefore improve its reliability and repeatability. This section title sets up the context to improve the stability of the T-distributed stochastic neighbor embedding, TSNE, algorithm. This is a multiple-choice question testing your knowledge of how to make TSNE, a visualization algorithm, more stable and reproducible. Think of it like trying to take a really good photo. You want the same great shot every time, not something different depending on the camera settings. This question asks you to pick from several options those that make your TSNE results consistent across different runs. It's about getting reliable, repeatable visualizations. I recommend this because more iterations give the TSNE algorithm more chances to settle on a good solution, thus reducing the impact of the random starting point. It's like giving a puzzle solver more time. They're more likely to find the best solution. I strongly suggest this. Setting _random_state controls the randomness, providing a reproducible result every time you run the code. It's like using a specific recipe. You get the same result each time. TSNE is short for T-distributed stochastic neighbor embedding. _random_state is a parameter that essentially fixes the random seed, removing the randomness from the algorithm. These are the methods to address the instability and lack of reproducibility in TSNE visualizations. This allows the algorithm to refine its solution over more steps, leading to more stable results. This is crucial for reproducibility. By setting this, I guarantee the same random numbers are used each time. I will skip this row because it's not relevant to the explanation of lines 16 to 20. This sets the context. TSNE results are unstable because of its random nature. The goal is to find ways to reduce that instability. The overall goal is to improve the consistency and repeatability of visualizations created using the TSNE algorithm. I'm tackling how to make the results from TSNE, T-distributed stochastic neighbor embedding, a visualization technique, more consistent and reliable. TSNE is a bit unpredictable because it uses randomness, so I need to figure out how to control that. I'm asked to find ways to make my TSNE visualizations less sensitive to random changes during the algorithm's calculations. I can improve TSNE's stability by running it for more iterations. Think of it like this: each iteration is a step toward the final picture. More steps mean a better chance of getting a clearer and more consistent final result, less affected by the random starting point. The _random_state parameter is like setting a seed for the random number generator. It ensures I get the same sequence of random numbers each time, making the entire process reproducible. This is the most direct way to remove the influence of random starting points. A lower learning rate makes TSNE take smaller steps toward the solution. This can sometimes improve stability, but it's not a guaranteed fix for the randomness in starting conditions. It's more about the pace of the process than the core issue of unpredictable initial points. I'm using TSNE, a method for visualizing high-dimensional data. However, I'm noticing some issues with consistency in the results produced by TSNE due to its reliance on random starting points. My goal is to select methods to reduce this randomness in the output. Perplexity controls how TSNE considers nearby data points. While a good perplexity is needed for good results, changing it won't directly improve reproducibility. It's a different aspect of the algorithm. These are the options I am given to explore in order to solve the instability issue in TSNE. This quiz focuses on how to make the results from T-distributed stochastic neighbor embedding, TSNE, a visualization technique, more consistent and reliable. TSNE is a bit quirky because its results depend on random starting points. We'll explore ways to reduce this randomness. I think of this like refining a sculpture. More iterations give TSNE more time to tweak the visualization. It starts with a rough shape and, with more iterations, gets closer to a final, more stable form. This reduces the impact of where it started. It's like giving it more chances to find the best arrangement. This is like setting a seed for a random number generator. Think of it as having a specific recipe with the exact ingredients for creating the visualization. Now, every time I use this recipe, using the same seed number, I will get the exact same visualization. This makes your results repeatable and shareable. It's all about control and predictability. I recommend reducing the learning rate. A smaller learning rate means TSNE will take smaller steps towards the final arrangement. While this can lead to improved stability, it might not completely solve the issues from random starting points because it primarily impacts convergence speed, not initial randomness. It's a helpful tweak, but not the main solution. Increasing perplexity doesn't directly tackle random starts. Perplexity controls how many neighbors each data point considers. While it affects the visualization quality, it does not guarantee more stable results from one run to another because it's focused on local neighborhoods and doesn't address the issue of random starting points. It's a good parameter to adjust for quality but not for reproducibility. This question focuses on how to make the results of T-distributed stochastic neighbor embedding, TSNE, a visualization technique, more reliable and consistent. Think of it like taking a picture. You want the same picture every time you take it, not different versions due to random effects. TSNE is a bit tricky because it's a stochastic algorithm, meaning there's a random element involved, and this can lead to different results each time you run it. We'll explore ways to control these random variations. This is a multiple-choice question designed to test your understanding of how to improve the stability and reproducibility of TSNE results in Sklearn, Sklearn, a popular Python machine learning library. We'll look at different parameters you can tweak to get more consistent visualizations. I see this option as a key to better stability. The TSNE algorithm iteratively refines the positions of data points in the low-dimensional visualization. More iterations mean the algorithm gets more chances to find a stable solution, reducing the impact of the random starting point. Think of it like repeatedly shaking a snow globe. Eventually, the snow will settle into a more consistent pattern. This one directly tackles the randomness. The _random_state parameter sets a seed for the random number generator. Think of it like setting a specific starting point for the algorithm. If you always use the same seed, you'll always get the same sequence of random numbers, leading to the same final visualization. It's like having a recipe. Following the same steps every time gives you the same result. Increasing perplexity changes the neighborhood size that the TSNE algorithm considers. This can improve the quality of the resulting visualization but doesn't directly address the randomness issue. The focus here is solely on making results repeatable. Decreasing the learning rate makes the algorithm converge slower. While slower convergence sometimes leads to slightly more stable results, it's not a guaranteed fix for the inherent randomness of TSNE. It doesn't get to the root cause, which is the random initialization. I'm tackling the challenge of making TSNE visualizations more reliable. TSNE, or T-distributed stochastic neighbor embedding, is a powerful tool for visualizing high-dimensional data, but it has a weakness. Its results can change dramatically depending on how it's initialized. I aim to find strategies to make these visualizations consistent and repeatable. Lowering the learning rate might help stabilize TSNE's convergence, but it's not a surefire fix for the randomness of the starting point. It could slow things down without actually solving the core problem. Think of it like this: you're trying to reach a specific mountain peak. A slow walk, lower learning rate, might prevent you from getting lost, but if you start far away, it still takes more time, even if you finally reach the peak. Setting the _random_state parameter is like giving TSNE a specific seed to its random number generator. It's the most direct way to get the same results every time you run the algorithm, provided you keep everything else unchanged. It's like making sure that you use the same set of instructions each time, getting the exact same output. Giving TSNE more iterations lets it refine its results over more steps. This helps it overcome the effect of a potentially bad starting point and settle into a better visualization, thus creating more stable results, less dependent on its initial random positioning. It's similar to giving a GPS more time to find the optimal route, resulting in a more accurate and consistent path. Perplexity in TSNE influences the local neighborhood it considers. While important for the meaningfulness of the results, it doesn't directly control the random initialization. Changing it won't necessarily lead to more reproducible results.